So let's jump back in to the math here. We were talking about Taylor's theorem, which you see in front of us here. So I got through the first order Taylor's theorem, which you can see in front of us. And I talked about it conceptually. I talked a little bit about conceptually what the second order Taylor's theorem is. But before we start writing it down more precisely, I think I want to do an example of working with this formula for the first order Taylor's theorem, okay? So here we're going to want to determine the first order Taylor formula for this function here at this point here, 0, 0, okay? So we need to be given a function and a point. So let's look back here. We need to be given a function, that's this f from Rn to R, and this function, this point here, a in Rn. So in this case, we have a function from R2, so that's 2 inputs and 1 output, and then it has, we're given this point, which is the origin, 0, 0. Okay. So how are we going to do this? Well, if we look at the formula here, we're going to need to compute the partial derivative with respect to each variable. So we're going to compute the partial of f with respect to x. This is going to be 3 times e to the x, y, or oops, 3 to the 3x plus 2y. And then df dy is going to be 2e to the 2x to the 3x plus 2y. Right? So there's just a little chain rule there that happened to get that. Okay. So that's the partial derivative here. The two partial derivatives. What else are we going to need? Well, we're actually going to end up plugging in that number a into the, or that point a into these partial derivatives and also into the original function. So let's see, at a, so at the origin, in this case, a is 0, 0. So at 0, 0, this is going to be e, or 3e to the 0, so that's just 3. And then over here for df dy, again at the origin, this is 2e to the 0. And so that's just going to be 2. Okay. And then, like I said, we also need f of a. So this is just me so far gathering all of the information I'm going to need to fill in that formula that we saw on the previous slide. So this is going to be e to the 3 times 0 plus 2 times 0, which is just e to the 0. So that's just 1 here. Okay, so I think with this, we can fill in the remaining stuff here. So this function, I know this function looks like, it's kind of hard to keep track of what this is a function of, but remember, a is a given point, so it's fixed. The only variable here is h. So h is actually our variable. So maybe I'll even highlight that back here if you want to add that to your notes. So h is the variable. This is the variable. Okay. So in this case, what we're looking for is f of 0 plus h1, 0 plus h1, comma 0 plus h2, right? So that these zeros are coming from this point a here. So it's 0, 0. A is the point a is given by 0, 0. So that's why we have 0 and 0. And like I said, and like I just said a minute ago, h1 and h2, those are our variables. Or you could think of the vector h1, h2 is the variable. So in this case, the vector is going to equal h1, h2. Okay. Now in this case, the zeros are kind of just adding extra unnecessary notation. So I'm just going to write, you can maybe sometimes we even write this as f of h1, h2. Okay. It's not uncommon. In fact, I was looking over the homework, and there's several problems where you're looking at the Taylor formula at the origin. And so this is gonna be kind of common where the zeros just kind of go away. But if you're looking at it somewhere else, say at 1, 0 or something like that, or 1, 1, then you're gonna have extra stuff being added like this. Okay. In either case, we can now use the formula to fill in the rest, right? So remember, we're imagining h1 and h2 are small numbers, so this is close to the origin. So basically, it's almost just f of 0, 0, so f of 0, 0. But then we have to add to that h1 times the derivative with respect to x at 0, 0 time, no, that's it, plus h2, and then the derivative with respect to y at 0, 0. Okay. So these are this is our, our like fixed term. This is the basic term. We're saying, okay, well, we're near 0, 0. So f of something near 0, 0 is going to be roughly f of 0, 0. And then we have our two first order terms. And then we throw on this extra r1 of 0, 0, and then h. Okay. Cool. And now we're going to fill in these things here. Okay. We're going to fill in this and this, and this. F of 0, 0, and then the two partials, which is what we did up here to start. So f of 0, 0 is 1 plus h1 times 3 plus h2 times 2 plus, and then this we can't fill in, so we just leave it alone like that. Okay, cool. And that there is kind of how you'd go about filling in one of these things. Cool. Any questions on that? So I think, it's not too bad once you have the formula in front of you. Okay, like you can just fill it out. A lot of times these formulas end up looking scarier than they actually are, especially when we write them in terms of, like n dimensional, right? If we don't have a fixed dimension, if we don't have a specific dimension we're working with, then this formula is going to look really scary because there's a lot of unknowns like the dimension. So we end up using the sum notation and a lot of stuff gets hidden. But when we have a fixed dimension, it actually is not too bad. So for example, here everything's two-dimensional, so everything works out. It's just a couple of partial derivatives, add it all up. Cool. So our answer here will contain variables h and r. So yes, I'll say yes and no because it contains h. So h are the variables for sure, 100%. So h1 and h2, or you could think of it the vector h. These are our variables. And notice that r1 is actually a function itself, which depends on the point and the variable h here. So this, you can think of r1 as a variable, but it's also it's a function that's taking in that you can think of it as a variable that depends on these other variables already. Okay. Cool. Yeah. So it's like I think of it as like the error term. If we stopped here, if we left off this term, this here, these first three terms are basically they're a linear approximation of this function near the origin. So if I was looking at near the origin at this function, I plugged in small numbers for h, then this here would give us an approximation for plugging in those numbers up here. So for example, like 0.01 or 0.1, 0.01 comma negative 0.01 or something like that. Plugging that in here, that looks ugly and it's hard to deal with, but here what this is telling us is it's basically just this here. It's basically 1 plus 0.01 times 3 and negative 0.01 times 2. And then this is just saying, but it's not quite equal to that. Like if you want to put an equal sign, you need to throw in the error term. Okay, cool. Yeah, so this is, but it is good to point out that your final answer should still depend on the H's, okay? And then the R is just gonna kind of sit there. The R stuff looks scary, but and you know, for all practical cases, it's just gonna sit there. You just write it and it just sits there, and you just kind of leave it alone, and you don't ever simplify it or anything. Okay. So this was the first order Taylor's approximation here. Now we want to talk about the second order. I mentioned a little bit yesterday that the first order you can think of as approximating your function with a plane, and what we're doing with second order is we're going to approximate f of x, f with a curve now instead, a parabolic curve. So f, maybe I'll write it in orange here. So f again goes from Rn to R. Okay. And we have, we want to write f of x plus, or maybe a plus h. So again, a is a point in Rn. So a lot of the setup is the same, and an h is equal to h1, h2, up to hn. Okay. And formula itself is going to start off very similarly to the other formula. So we have f of a, right, plus the first order terms are still going to be there. I goes from 1 to n of hi times df dxi. So the first order terms are the same. But before we get to our error term, we're going to add more information about the function. In this case, it's going to be what we call second order information, which is just information having to do with the second derivatives. And so here we're going to get, so we have this sum is going to be summing over two variables. Basically, we have these two variables, I and j, and each of them independently is going to go from I to, from 1 to n. Okay, and there's going to kind of be, they're both kind of going to be balancing each other. And we'll see an example of this so we can get comfortable. And basically, this is going to say, okay, now we're going to have both hi and hj, and then we're going to say, okay, d squared f over dxi dxj. Let me make sure I got that in the right order. I think it doesn't matter, but right, it doesn't matter, but okay. And then we're going to add to that R2 of AH. Okay. That there is our thing. So the new term here is this will be the second order term. So again, this is new to the second order. And also technically this R is a different R than the first order stuff, naturally, because this should technically be a better approximation, this first three terms here. And so this R2 should be a different R than R1. So it should be a different R. But again, it's at this point in time, it's just notation. Okay. So if we're following along at home, you have maybe some curve. Okay. And you have a point on the curve like this. Okay, again, this here is A, and this here is f of A. Okay, and before we drew a little tangent line, so let me go back 2 slides. On our picture, we drew a little tangent line. Here, what we're going to do is we're going to draw kind of this curve that is parabolic, but doesn't quite follow the exact same curve, but it kind of curves near here, near this point A. It kind of curves basically the same as this, and it should be like touching at that point. So let me make sure it's actually touching at that point. But you notice the further away we get from A, obviously the worse of an approximation this gets. So if I were to plot, if I move over, I think I used purple last time, so I'll stick to that. So if you move over by H, so this here is A plus H. So then you go up here. This is f of A plus H, and this is what our these first 3 terms are giving us. Okay, these first 3 terms are telling us this point up here. And so, of course, the error term R2 is giving us this little distance here. So this is R2. Okay. Let's see. I'm trying to zoom in a little bit so you can see a little better. Okay, cool. So just wanted to zoom in on this picture a little bit so you can see. Okay. Basically, it's the same picture as what we saw up here, except instead of a tangent line, we're using this curve here. So one thing I wrote last time is that this here gives this curve here, right? So we have f of A plus this stuff. If you break this down, you end up with basically this is a quadratic polynomial in h1 through hn. So if here we had kind of everything was linear in terms of the h's, down here everything is going to be quadratic in terms of the h's. So you can imagine, we're not really going to discuss it much in this class. You can imagine that we could very easily define what a third order Taylor formula would be, or fourth order, whatever order you want. And it would just get higher and higher degree, and it would just get more and more complicated, more and more terms to do. But for the sake of this class, we're only going to do the first order and second order. If you've taken, I'm trying to remember what class you learned this in, I think probably like 9C, you learn about like Taylor polynomials, right? And this is very much related to that. Those Taylor polynomials are approximating some one. So in that context, you're learning about everything in one dimension. So n equals 1. And so the formulas are much less complicated in that situation because everything is one variable. But basically, this picture kind of encapsulates that. So first order one is approximating with a line. The second order one is approximating with a curve. And then with like basically the curve, as the degree gets higher, the curve gets closer and closer to the blue curve here. So the orange curve would get closer and closer to the blue curve here. Okay, cool. Any questions about this? You want to jump into an example? Let's jump into an example. Okay. I don't think I have anything else to say about that. So let's calculate the second order. Here I wrote approximation. I think usually in the homework it says Taylor formula. So maybe I'll write that. I'll say, because I think that's better, more appropriate. Second order Taylor formula of this function here, sine of xy, again at 0, 0. Again, like I mentioned earlier, on the homework, a lot of them are around 0, 0, and it just kind of makes the formula a little nicer. So again, we'll start by computing some derivatives. So we'll take the partial of f with respect to x, and we get y cosine of xy, the partial of f with respect to y, and we get x, or negative x sine of xy. And this is going to be this derivative here. We have to actually plug in this point. So d of x, df dx at 0, 0, in this case is just going to be 0 times cosine of 0. So even though cosine of 0 is 1, we still get a 0 because it's times 0. So df dy at 0, 0 is going to be negative 0 times sine of 0. So this is also 0. And then we want to actually plug in 0, 0. And we get 0. So we're going to get a lot of zeros here. But in this case, we want to compute second order information as well. So we also are going to need we're going to need all possible second derivatives. So in this case, I'm actually going to move this here up. And we're going to say we want to start computing the second order derivatives. So df d, so all possible. So maybe I'll write using that other notation. F of, so this is fx, this is fy. If I want fxx, this is going to be the derivative of this with respect to x. So basically I get negative y squared sine of xy. So I took the derivative of this with respect to x. And then I take fxy. Now the derivative of this with respect to y. Actually, I'm going to need more space for that. Fxy is going to be a little more complicated because I have a y here and a y here. So I have to use a product rule. So this becomes cosine of xy plus, probably a minus xy sine of xy. Okay. And then over here, I'm going to write f of y x. And then here's f of y y. Actually, I'm running low on space. So f of y x, f of y y. These are the two I have left. So the derivative of this with respect to x, again, that's going to be a product rule. So negative sine of xy minus xy cosine of xy. Again, I'm kind of doing, not necessarily spelling out a lot of the steps for the derivatives I'm taking. So if you're wondering what I'm doing, you can write this down and check my work later to make sure I did it correct. Or, if you can keep up, then you can check my work now and make sure I'm not making any silly mistakes. Now we take the derivative of this with respect to y. So then we get negative x squared cosine of xy. Okay, so these are the four second order derivatives here. And I'm going to write them, we have to plug in 0, 0 in order to actually use them in the formula. So we plug in 0, 0. In this first case, we just get a 0 because there's a multiplying by 0 up front. In the second case here, this is, I think, the only time we're not going to get 0. So cosine of 0 minus 0. So we just get 1. And fyx at 0, 0 is going to be sine of 0 times something, or minus 0 times something. So this is all going to be 0. And then f of yy at 0, 0. There's a negative x squared here, so this is going to be 0. So a lot of zeros in this problem. I'm probably going to do another example where we actually get something here. Oops. Come on. What the heck? Okay. Okay. Not gonna let me do that. Okay, so now we have this is the only non-zero thing. So we're going to want to write f of h1, h2. Remember, it should be 0 plus h1, comma 0 plus h2. But the zeros in this case go away. And so we get f at 0, 0. F at 0, 0. So we get 0 plus h1 times 0 plus h2 times 0. Okay. So these are the first order terms, right? So far, we're just getting a whole bunch of zeros. Now let's look at the second order terms. So the second order terms, again, what we're doing is we're going through every possible combination of variables, every possible combination of two variables in both orders, right? And so in this case, we're going to get h1 squared times 0 plus h2 squared times 1, or no, that's going to be h2 squared. This is h1 times h2, so h1 times h2 of 1 times 1. Actually, let me make sure. So remember that the order switches. So h1, h2 should go with d squared f of d y, or no, dx dy, but this here is dy dx. So this should actually be, this one should be paired with this one, the awkward thing of switching the orders by using the different notation. Remember, the orders are in the opposite. These are in the opposite order. And so then h2, h1 should be paired with fxy, right? Because this is here is df, d squared f dy dx, right? And so the order in the formula, the order here matches the order here using this notation. If this was in the other notation, this would be f xj xy, or x1 xi. So this is in the opposite order. So this is times 1 and then plus h2 squared times 0. So a bunch of this goes away, and then we should plus our R2 stuff. So the final answer is going to be, in this case, it's going to simplify a whole bunch, and you just get h2, h1 plus R2 of 0, 0, comma h. Okay. So this one simplified a whole lot, right? Cool. Any questions on that? Okay. I think I do want to do, so df dy of original, is that right? See this here. Oh yeah, no, that's totally wrong. That should, for some reason, when I switched the variables, I switched this to a cosine, and so that should totally be, let's change color here. That should totally be just cosine here. And so we get 0 cosine of 0. So that still works out here, but how does it affect over here? It won't affect this because that's this, but that will affect this here, these two here. So let's see. Good catch. Thank you for noticing that. So here we get the derivative of this with respect to x is going to be, again, cosine of xy minus xy sine of xy. Yeah, I should have noticed that. I should have noticed that sooner, right? Because this and this are supposed to be the same, right? These two are supposed to be the same. And so I should have noticed sooner that there was something going on there. And this here would be the derivative of that with respect to y, which is now x squared, negative x squared sine of xy, which, so in this case, when we plug in 0, 0, we still get 0 here, but up here we're going to get 1, just like we did up here. Okay, so one of these terms is going to be different. So this term here is also going to be a 1. And so I can fix this thing. Right? So I wrote h1, h2 as separate from h2, h1, but they're the same because, multiplication commutes. So I can just multiply everything by 2. Or not everything, but just that term can be multiplied by 2. Okay, cool, good catch. In red here, I've written all the changes there. I made a mistake way at the beginning, right? We've all been there. Okay, cool. Good catch, good catch. Cool. So I guess before we jump really into it, because like I said, there's a lot to cover. I want us to remember when we were finding, in single variable calculus. So remembering from single variable calculus, the main way we would find extrema, right? So extrema is like this fancy word for minimum, for like a minimum or a maximum. You'd call it an extremum, and then plural becomes extrema. And so you'd look for places where the derivative was 0, right? So for example, here, the derivative would be 0, and over here, the derivative would be 0. And these are what we'd call relative extrema, right? For finding global extrema, the task was a little different, and we'll talk a little bit about that next week. But the first strategy was to find where's the derivative equal to 0, okay? And now it wasn't always the case that you ended up with finding the derivative being 0 doesn't always give you an extrema. Doesn't always give you a minimum or maximum. It can do something like this, and we'll see a little bit more about that. And if you remember, the trick to finding these was the second derivative test, and so you have to use that. But in this case, we're not going to. The second derivative test is a lot more involved, and so let's start by just finding an analogy for this, which, if you remember, was the first derivative test. Take the derivative, set it equal to 0, and figure out where those points are. And so that's what we're going to start with today. So I guess I should have mentioned a function here. So f, we're going to say, is one of these smooth nice differentiable functions from Rn to R, scalar value vector of several variables. And we're going to say a point in the domain of this function is going to be a local maximum if there is a neighborhood around A such that f of x, or f of A, is bigger than or equal to f of x for all x in this neighborhood. So neighborhood, I put in quotes here, but it actually does have a very specific definition. Basically, a neighborhood around a point A is just like you take a little disk around that point. So if you take A to be a point in R, so for example, on this page, it would be in R2. So this here is A. Then a neighborhood of A would be something that looks like this. So this here would be a neighborhood of A. So this is a neighborhood. And neighborhoods can be really small or they can be big. So what this is saying is that there's some neighborhood, maybe it's kind of small, but there's some neighborhood where in the domain where everything around that, A makes it makes the function as big as possible. So it's this notion of, so if I have kind of this in one dimension, we have pictures like the ones on the previous slide. So we'll have something like if this is your function f, right? Which shoots up like that. If you have a point A like this, so this here is A, right? Maybe, if you go far enough, there's points where you get much bigger than this point F of A. But if you just say like, hey, let's just restrict to a little neighborhood here, right? This here is a little neighborhood, a one-dimensional, this is a two-dimensional neighborhood. It looks like a disk. A one-dimensional neighborhood is just a little interval around A. Then we get, okay, if we just look around here, now A is definitely bigger than everything inside of here. F of A is bigger than everything inside of here. So somewhere over here would be F of X. Okay. That makes sense. And similarly, we can say A is a local minimum if there's a neighborhood there. So if F of A is less than or equal to F of X for all X in the neighborhood. Okay. Cool. So we call the general term for, whether you're talking about a minimum or a maximum is called an extremum. So it's, you should think extreme. Extreme is like kind of like when you think of like the extreme cases, it's always like the ones at either end. So minimum and maximum are kind of extreme cases because it's kind of like as big as it can be or as small as it can be. And we use that extra adjective either local, like we have here, or we can also say relative, because that's relative to this little neighborhood. So relatively speaking, this is a maximum, or relatively speaking, this is a minimum, right? Cool. Okay. Okay. Now the question is like, so this is like, okay, we can get a geometric picture of what's going on. You can imagine it in if n equals 2, then the graph, right, lives in 3 dimensions. So we have like the xy plane, and then you have kind of the graph living up here. A local maximum would look like the peak of a little hill, and a local minimum would look like the peak of, or like a little valley or something like that, or a little something like a little, the very bottom of like a little dip in the graph or something like that. And so that's harder to draw, but you can still get the idea. There's like a peak, and there's like a little valley. Okay. Or you can just use the symbols and think of it numerically, because as we get into higher dimensions, then finding the then you can't really draw a picture of what's going on. For example, in the analogy, or not the analogy, but the example I gave sometime earlier this week, was that you can think of a function from R3 to R as being like the temperature at a certain position in 3-dimensional space. And so the maximum would just be the hottest point in the 3-dimensional space. So wherever the hottest point, or relative to the nearby. So like if you have the kind of like this hot spot that's like really hot, and then it's just hotter than everything around it, then that point where it's the hottest in that little spot is going to be a local maximum. Even though there's maybe something hotter way out here, right? If this point is kind of hotter than everything around it, then that's going to be a local maximum. Okay. You can think of, I picture it like with like in like infrared, right? You have like the red, there's like red symbolizes super hot, and then like blue symbolizes not so hot. And so you kind of think like that big red hot spot is going to be like a maximum. Okay, cool. So let's talk some more about how we would actually go about finding these. So I can define these, but then how do we actually go about like finding where the local minimum and maximum are? So just like in the single variable case, right, we had what we called a first derivative test, right, which was figuring out where we might have, like, where's the derivative equal to 0? That's going to tell us where we might have a maximum or a minimum, or just an extremum in general. So let's look at the first derivative test. So you have this differentiable function, and you know it has an extremum at a. Then you can conclude that the derivative, I shouldn't say the derivative, the total derivative of f at a is equal to 0. Okay. Now notice that the total derivative here, that should be a matrix here. So this is the 0 matrix, right? So when I just wrote it as 0, but you should be thinking this is the matrix with all zeros. And I say matrix, but this is right scalar valued, so it's just going to be a row matrix. So you could think of it. I could have also said this in terms of the gradient. So another way to say this is that all partial derivatives are 0 at that point, right? Just like in the single variable case, right? If, for example, if n equals 1, then this is just a 1-by-1 matrix. And so you're just saying that the derivative of that matrix is equal to 0. But as soon as you introduce more variables, then you have to check all possible partials and make sure that they're all equal to 0. Okay. Cool. Now, this is how typically we would state, like in the math textbook, this is how it gets stated. If you have a function where there is an extrema, then the differential or the total derivative at that point at the extremum is going to be 0. But the way we actually use it is we use it to find the list of candidates. So solutions, points in Rn where df is 0 are candidates for extrema, right? Because let's think about this in like a procedural way. Like you're given this function and you said, hey, find these extrema. You're like, well, I don't even know where to start. There's infinitely many points to check. Well, you can set up an equation and set it equal to 0. And then now you have this equation, and so it's actually going to be n equations with n unknowns, right? Because it's going to depend on x1 through xn, and you're going to get n different equations here in the gradient, and you set them all equal to 0. And so you can maybe you can maybe even narrow it down to 1 point, but maybe you narrow it down to 2 or 3 points if in some, because these are not always going to be linear functions, so you might have multiple solutions. And so if you get that, then you might have just a handful of points, and you're going to say, okay, now we can check these to see if they are extrema. Okay. Cool. Any questions about this? Any questions about this first derivative test? We'll see an example in just a second. Okay, cool. So let's go ahead and move on. Again, if you have questions, feel free to slow me down. I'm going to go jump into this example. So we're going to find the critical points of this function and determine whether they are minima, maxima, or neither. Okay. Like we said before, just because you find, I knew I was going to forget to write this down. So I used the word critical points here, and I never told you what that meant. So I should say solutions. So like I said, the general structure of this is we're going to take the derivative of f, the total derivative of f, set it equal to 0, and solve for the different values of xi, and those are going to be our candidates, and we call these candidates. So solutions to df equals 0 are called, and I spoiled it with the problem. They're called critical points. Okay. And that's going to be where that's going to be what we look for. We're looking for critical points. So the gist of the first derivative test is look for critical points and try to figure out if those are, once you have those, you've narrowed down your list of possible extrema. Okay. So here we're going to do this and we're going to say, okay, so we want to find the critical points. So we need to compute df. So, well, that's just going to be the matrix of partials. The only one possible output, so it's going to be a row matrix. Here we're going to get 2x and we're going to get 2y, and then I'm going to double check because of the mistake I made last time. So better to double check now. Yeah, so the derivative of this with respect to x, this goes away and I just get 2x. The derivative of this with respect to y, this goes away and I get 2y. Yeah, okay. I'm confident with this. Okay. And now if I want to set this equal to 0, I'm setting it equal to the 0 matrix. Okay. So that means I'm solving the equation 2x equals 0, 2y equals 0, the system of equations 2x equals. In this case, it's just two equations, and they tell you that x equals 0 and y equals 0. Okay. So there's a critical point. So f has a critical point at 0, 0. Okay. Okay. But now we need to determine whether or not it is whether it's a minimum or a maximum, or if it's neither. Okay. So this one's going to require just a little bit of like thinking here. So f of 0, 0, we don't really have any tools for determining this part yet. So we're just going to kind of logic our way through it. And so f of 0, 0, first of all, is 0. But then what observation can we make about f of xy equals x squared plus y squared? Well, if we plug in anything that's not 0 into here, whether it's negative, positive, or whatever, we're going to get something positive, right? So this is positive. This is greater than 0 if, if xy is not equal to 0, 0. So what does that mean? That tells us, right, that this is going to be smaller than every other point. So that implies that 0, 0 is a minimum. Okay. Right, because every possible output of this function is going to be positive, or at least it's not going to be negative, I should say. And the only time it's 0 is if you plug in the origin, and every other point is going to be positive. And so you can see that 0, 0 has to be a minimum. Okay. So this is just a little way for us to practice the first derivative test, just to find the critical points. And in this case, it happens to be that we can realize that critical point is actually a minimum. But this is not super satisfying because it almost feels like we just got lucky. Okay. And in fact, we just got lucky that this function, well, we didn't get lucky. I chose it for us to get lucky, that this function here happens to be a function that spits out positive numbers. And so by finding a critical point where the output is 0, then we know it has to be a minimum. Okay, so that's just a coincidence, right? But we need a systematic way to figure out, okay, we know how to find critical points, take the derivative, set it equal to 0. How do we determine if that critical point is actually a minimum or a maximum or something else? Okay, so what are the options for something else? Well, it could be a point of discontinuity for the derivative or something like that. But then the other thing we're going to look at is something called saddle type points, and we'll talk more about that on a later slide. Okay, cool. Any questions on this sort of problem? The important parts of this is taking the derivative and solving for x and y. In this case, taking the total derivative and solving for x and y. This case, we got pretty lucky here with the points we chose, with the points we got, and so we can kind of see that. So the solving it wasn't too bad. But we'll see. I think in a couple of slides, we're going to get to some other examples, and it's not always going to be the easiest part. Okay, cool. Okay, so again, the next thing we want is a strategy. Once we have the critical points, finding the critical points we now know how to do. But once we have them, how do we determine what they are, or how to classify them? That's usually the language that gets used in the homework. How do we classify those critical points? Are they minimum? Are they a minimum? Are they a maximum? Or are they neither? Okay. So we need to build up some machinery first. So the first derivative, the analogy for the first derivative was the total derivative, the matrix of partial derivatives. Now we're going to introduce this other matrix. It's called the Hessian matrix or the Hessian matrix, depending on how you pronounce it. The Hessian matrix is, if you think of the total derivative as the matrix of partial derivatives, this is the matrix of second derivatives. So that's not like in this case, that's not like a formal name, but I like to think of it that way. So this is the matrix of second derivatives. So the analogy here is that this is going to take the place of our second derivative from single variable calculus, except that we'll see that the second derivative test is going to be much more complicated in this case. And so it's going to take us a little bit to build up to it. Okay. I don't know if I'll even get to it as deeply today. So let's start by just filling in what this matrix needs to be. So basically what we're going to do is we're going to take every possible second derivative in every possible order. Even though the mixed derivatives that we know are the same, we're still going to write them separately in this. Okay, so this is d squared f dx1 squared. Okay, and now we're going to take the derivative. So the rows, so the hard thing is remembering which one is which, but basically down here, we're going to say this is going to be d squared f dx2 dx1. So the order here, so how do I remember the order here versus the order here? So if you can imagine up here, we're going to put df squared dx1 dx2. So the opposite order. How do I remember which one goes here, which one goes here? So the order here is row, column, row, column. So this is in the second row, the first column. So it's dx2, dx1. Over here, this is first row, second column. So we have dx1, dx2. So for example, over here, I'll write it dxi, dxj. This is going to tell you the row, and this is going to tell you the column. Okay. And this is going to keep going until you get to d squared f. Let me write that a little nicer. D squared f dxn dx1. And if you're jotting this down and you're like, I'm going to use the other notation, remember that the other notation the order switches when you write it. So because you're always working from the inside out. But since this stuff happens on like the right hand, this happens on like the left hand side, so it goes from right to left. If you're using the other notation, it's going this way, so it's going from left to right, and so you've got to remember that. So over here we have d squared f over dx1 dxn. Okay, and the columns follow suit, and so you can kind of extrapolate until we get down here to dxn squared. Okay, so you can imagine along this main diagonal is all of the derivatives with respect to the same derivative twice, or with the same respect to the same variable twice. So dx1 squared, dx2 squared, dx3 squared, so on and so forth. That's along the diagonal. And then because of the law of mixed partials, any entry down here is going to be mirrored up here. Okay, you're going to get the same thing across the diagonal. Okay, so this looks big and scary when I write it like this. Okay, and we're going to see, most of the time n is going to equal 2, maybe equal to 3. It can equal as big as we want it to be, but typically in this class we've been pretty good about just restricting to like 2 or 3. And so these matrices you'll actually end up working with won't be 15 by 15. They'll be like 2 by 2 or 3 by 3. Okay, cool. So you may remember that there's an equality of mixed partials. So, and I made a big deal about like, okay, this is the row and this is the column. So make sure you don't flip these. But because of that equality of mixed partials, if you mix them up, it's not going to be the end of the world once you actually compute things because they're going to be the same anyway. Okay, cool. So this is the Hessian matrix. This, for now, is going to be our placeholder for the second derivative. But it turns out that then using that second derivative to kind of come up with a second derivative test for testing critical points to see if they can actually be minima or maxima actually ends up being more difficult, and you end up having to work for it a little more, even once you take the Hessian matrix. And I'll talk a little bit more about that right before we talk about the Hessian, the second derivative test, which we might get to right at the end today. Okay, cool. So this is the Hessian matrix. Before we start doing stuff with it, let's just practice actually computing this thing. So let's compute the Hessian matrix for this function right here. So this is this crazy polynomial function. It's not that crazy, it's just long. And we want to compute the Hessian matrix for this guy. Okay. So notice this is in 3 variables. So it's, wanted to kind of give us a fair bit of practice. So it's a good size. So I like to start by taking, just like if you were taking the second derivative of a single variable function, you'd start by taking the first derivative of that function. So let's take the first derivative of this guy. In other words, let's find the matrix of partial derivatives. In this case, remember, these are scalar valued functions. All of the functions we're looking at for this section are scalar valued. And so we are going to end up with a gradient, right? It's a row matrix. So take the derivative of this with respect to x, we get x squared, right? So we bring the 3 down. So 1/3 times 3x squared is just x squared. And then 2xy, so plus 2xy. And that's it for x's. Now the derivative with respect to y, this goes away and we just get x squared plus 2yz. And then this goes away. So that's this term and this term have y's in them. And then in the z, we have these two terms here. So we get y squared plus, y squared plus z squared. Cool. We close that off. Okay. So this is the matrix of partial derivatives. Now we want what I like to call the matrix of second derivatives, or what we're calling the Hessian matrix. Notice I capitalize Hessian. Hessian matrix is named after a person, and so you always capitalize it. It's one of those things in math. A lot of stuff is named after people. So we have this Hessian matrix and we want to compute it. So we just computed the total derivative and now we want to compute the Hessian, which we can do here. So I'm going to give myself plenty of space. This is probably going to be too much space, but let's go ahead and start it. So the way I like to do it is, the reason I like to write this down is because this here is telling us the columns here. So we're just going to focus on each of these. This here, we take all possible partial derivatives of this guy, and that gives us the first column. Then the partial derivatives of this guy gives us the second column. partial derivatives of this one gives us the third column. So focusing on this here, that gives us the first column over here. So that's going to get, we start with respect to x, and we get 2x plus 2y. Okay. Then with respect to y, we just get a 2x. And with respect to z, we get 0. Okay, because this doesn't change with respect to z. And then this first term doesn't change with respect to x, to y, so only the second term gives us anything with the y. Okay, cool. Hopefully we're okay on like partial derivatives at this point, right? Things like of especially functions like this. So okay. So now let's look at the second column. This here is going to give us the second column. Take the derivative with respect to x of this. Here we just get 2x. The derivative with respect to y, we get 2z. And then the derivative with respect to z, we get 2y. Okay. Now the derivative with respect to x, y, and z of this last one. So we just take all partial partials. So I'm going to squeeze it in here. So I gave myself, way too much space, but it's better than not enough. Partial derivatives of this. So with respect to x, that's a 0. With respect to y, that's 2y. And with respect to z, that's 2z. Okay, cool. And that's it. We're done. We can, if it's just asking us to compute a Hessian, we're done. But we'll see once you actually start doing the homework that that's usually not the case. It's usually going to ask you for a little bit more. But for now, we can stop here. I want to point out the symmetry of this matrix. So if you kind of draw a diagonal here, it has like reflectional symmetry. So this is the same, this is the same, and then this is the same. Okay, and that's always going to be the case for a Hessian, because basically what's happening on those diagonals, I talked a little bit about it in this slide, but is you have the mixed partials on either side, right? So this is d dx, or d squared x, and then you have maybe I'll use the f notation. So this is f xy, and this is fyx, and so then this is f xz, and this is fzx, and then this is f yz, and this is fzy, and so that's why the mixed partials are going to be equal like that across the diagonal. Cool. And if you've taken linear algebra classes, you know that we call this a symmetric matrix, and so there's a lot to be said about symmetric matrices, and it turns out that it actually makes our lives a lot easier when we actually go to try to define a second derivative test. Okay. Can you go back one slide? Yeah, I can go back here. So this is the general formula for the Hessian matrix. We saw computing it is just a matter of doing a bunch of partial derivatives. So that's what we did here. So I don't want to bog, I feel like I've given a lot of information already, so I don't want to bog you down with the actual second derivative test, but I want to talk a little bit about kind of the idea of it. So just again, as a reminder, in single variable calculus, you had, again, right, we learned how to find critical points. And so we have something like this. And critical points are just wherever the derivative is 0. So here we have a nice derivative equaling 0 because, the tangent line is horizontal. Oops. So all three of these are examples of f prime equals 0, right? I should say f prime maybe of a equals 0. In this case, a is just this point here. But if you remember the second derivative test told us about a property called concavity, right? Concave up or concave down. And so the second derivative test was telling us, hey, look, this goes down, this points down. So we call this concave down because the way we figure that out using calculus is we get f double prime of a is negative, right? And so every time we saw, okay, we found the critical points, then we take the second derivative. We figured out the second derivative was negative. That means we're concave down. So A had to have been a maximum. Now over here, we get concave up. And so we have the f of A is strictly positive that whole time, or maybe I should say, or equal to, because at that point it's going to be equal to. But basically all around A, on this whole little neighborhood of A, we had this happening. But over here, it goes, A is the point where it goes from concave down to concave up, which we called an inflection point. So A is, so f of A, f of, maybe I should say x here, and f of x, yeah, f of x near A, actually, no, sorry, I was confusing the first and second derivatives. So I'm going to go back to what I had. So f of A is negative, f of A is positive. And in here, f of A, f double prime of A is equal to 0 because it's going from pointing down to pointing up, right? So this was the second derivative test in single variables. What we're going to learn on Monday is the second derivative test in multiple variables. And it's going to involve the Hessian. And I'm just going to say now, it's a lot more complicated than this, right? These three pictures encapsulate the second derivative test for single variables. It is because you have more directions in the domain, things suddenly become much more complicated. And so we have to deal with this big Hessian matrix, and we have to do a little bit of linear algebra with it in order to figure out what is actually going to happen and whether it's a maximum or a minimum. And it's not always as easy as graphing and stuff because it's in higher dimensions. So, okay, cool. So we'll call it a day here.